Ziming G.
Thanks. I'd like to begin by thanking the organizers and by acknowledging my collaborators, Christian Copati, Lorenzo Di Pietro, Shota Komatsu. Today I'm going to talk about Tamiya mass gap with the entity stereo space based on this work with the same title. I'm Ziming Ji, I'm from CESA, and let's begin. So the focus will be studying mass gap in entity stereo space through its conformal boundary. So let us explain the question in more details. We start with asymptotic free theory, which is gapped in the IR in flat space. Then we put the theory in ADS fixed metric with radius L. By choosing different boundary conditions, we can realize either gapped or gapless phases. Then we vary the ADS radius L. The theory interpolates between weak coupling and strong coupling. Consistently with the flat space limit, gapped demands the gapless phases to disappear at large enough L. The question is, can we see this gapless gap transition from the boundary, and how? Try to answer this question by studying toy models in 2 dimensions, the first one being the ON sigma model at large n. So in flat space, as you may know, the ON symmetry is unbroken because there's no spontaneous symmetry breaking in flat 2D, so the theory is gapped. While in EDS, the curvature Q is IR divergence, so analog of spontaneous symmetry breaking is possible. We have additional massless phase. So if we look at the gap versus the ADS size, there's a red line massless phase, which has non-zero valves in general, which breaks the ON symmetry. From the larger computation, it can be seen that after a finite value of lambda L, the valve becomes purely imaginary, indicating this boundary condition being unstable. So what is the boundary signal of this? By using the boundary bulk OPE, we can look at the lightest operator in the boundary spectrum of the Haber-Statonovich field sigma, which is singlet under the unbroken ON-1. We notice that right at this point where the boundary condition becomes unstable, this operator singlet becomes marginal. We keep that in mind. And the second example is fermionic. It's Gros-Nivelle at large n. So in flat space, the vector ON symmetry is preserved, while the discrete axial symmetry is spontaneously broken by the fermion bilinear condensate. While in EDS, we can define either massless or massless by preserving either vector or axial symmetry. However, in this case, unlike the bosonic example, there's no signal of transition from the bulk equation alone. So we need to find the boundary signal. Inspired by the bosonic example, we look at the lightest operator in the boundary spectrum of the Haber-Statonovich field sigma again. Difference is that now sigma square is axial singlet. So we see that after some finite value of ADS radius, the dual of sigma square becomes marginal, while the dual of sigma touches BF bound, indicating the boundary condition being unstable afterwards. So we conjecture it is the boundary single operator being marginal that gaps the theory. And the application could be, for Yamuse in 4 dimensions, for example, there exists so-called Dirichlet boundary condition with boundary global groups and boundary currents due to gluons. We conjecture that some single operator under the unbroken SUN symmetry become marginal at some finite lambda L, destabilize this Dirichlet boundary condition, mediating quantum phase transition to confinement. Thanks.
Okay, fantastic. Questions? Oh, I'm good.
Have you identified the operator that becomes marginal in the case of anybody, in the case of Youngman's theory?
I'm attempting to say some trace J square, but yeah, we haven't done it. Thanks.